Well, here a couple of people from PDE discussed about this winter school, and even though we have idea, but we didn't carry it out. But Professor Kiahm actually made it, and we are really thankful for his effort. Okay. And I'm going to make 5 lectures on the regular theory of the partial differential equations. And let me first talk about what is a partial differential equation. So maybe you know all of them, but some of you may get confused about it. So partial differential equation is basically equation of partial differentials. You have a choice, right? So then let me start with a very simple equation, which is called Laplace equations. So let me use the black one. And Laplace equation is Laplace of u. And Laplace of u is basically the sum of second differentials. x1 squared, so n squared. And there are 2 ways to look at this equation. So one of them is this is basically the trace of second differentials. Okay, and second differential has a component like use of 1, 1 and use of n, n, and then you make a trace of them. And that is Laplacian. So this is a kind of partial information of second differentials. And this is a kind of linear partial information of second differentials. And then clearly we may think, well, there could be a nonlinear information about these second differentials. And the most general one could be like this one. So for example, you may think the determinant of this curve u, and that is called the Mozart equation. And or you will just this one has like lambda 1 to lambda n. You can diagonalize it because it is a symmetric matrix. Then you can consider the multiple of these numbers. And the lambda 2, lambda 3, and so on. So you multiply 2 different eigenvalues, and that is called the scalar coverage. And then we call it sigma 2. And if this is a principal coverage of the manifold, then this one is related with scalar coverage. And this one is related with Gauss coverage. So it's a very geometric. And or you may consider if this is eigenvalues, and if you write on it, and trace is invariant on the change of coordinate. So basically this one is the sum of eigenvalues of the second differentials. And let's say this is 0, then this one is like a balance equation of the second differentials. That's another way to look at the equation. So it's the balance of lambda i's. So
that's not equation, yes. That is not equation.
I made it 0, so it's equation.
Okay.
So here you can consider f. Okay. And so that's why even though you started the Laplace equation, then the basic theory can be applied to more general nonlinear equation, which is related with the geometric problems. And the other way to look at it is, as you know, this is like divergence of the gradient. Okay. So let's say F is a charge density. So let F be a charge density. And U is a potential function. So then, if you give me any domain omega, then I look at the total charge. Okay? And if you put the total charges here, then what's going to happen? You have high potential, then electric field will be created, so it goes up. So basically, the total charge will create electric flux. So then that one will be balanced with electric field, which is going out of the domain. U B sigma x. And then one of the ways to look at this electric field then is a gradient field of the potential function. So you may look at the gradient of U. Then this one will be gradient of U do E sigma x, and you apply divergence theorem, then gradient of U dx. So this is true for any omega. So you have Laplace equation. And this is the different way to look at the equation. So this is a balance equation. So this idea can be applied to fluid dynamics. Then you can derive equation of continuity, Euler equation, Navier-Stokes equation, and so on. So lots of equation from the physics comes from this point of view. Okay. So then here, if you want to create the balance, naturally the integral quantity is very important. So whenever you try to control the regularity of the solution, then you may look at the integral quantity. Okay. On the other hand, here it is more geometry. So you better compare your solution with the other geometric solutions to get the regularity. So even though you have same equation, but there could be two different ways to look at it. So and then the general case could be like the divergence of a gradient of U x is here. And then now we say this is the partial differential equation of non-divergence type. And this is divergence type. Okay, so I just try to introduce the vocabularies. Okay. So then, basically the 5 task is about the regular theory. And regular theory is very important to have an existence of solution and to control the behavior, and it shows up everywhere. And then I don't want the application that much, but I just try to concentrate how to get the regularities. So maybe in future winter school we may discuss, or somebody else will discuss how to use a regular theory to get more interesting stories like existence or dynamics and so on. But basically we will concentrate on the regularity. Okay. So what is the main philosophy to get a regularity? So we can start with the Laplace equation. Then if you look at the general PDE lecture book, PDE book, then you can find out it's the same thing even if it's analytic. Okay, the solution is very nice, basically. Okay. So then now you change the data. So many interesting data will comes in your equation. So maybe your media as a professor is discussed, or your diffusion may not be constant everywhere, or you may have geometry impact. So there could be a lot of different impact into your system or equation. So then such information will create different coefficient. For example, if you may handle with this kind of equation, linear equation, and that is a non-divergence type. Okay, and this is basically, you may look at the trace of the multiple of two matrix, and this is A sub ij. Okay, and this is non-divergence type, or you can look at the divergence type. So then clearly if Aij is delta ij, and if f is 0, then every equation will end up with a Laplace equation, and your solution is very nice. Okay. So now we try to perturb our coefficient. And then, so let's make some perturbation. Of Aij and F. Then we ask what happens to the solution. So what happens on the regularity of the solution. Okay, so that's the question. And then well, the problem, many things are well known. That's what I want to discuss. The first simplest case is, okay, well, if this is a fixed constant, then it's great. Then maybe I can change the A sub ij f with a very, very small amount. Okay? So that could be the first issue is a small perturbation. Of coefficient. Okay. So you can give some regularity on the coefficient. Let's say Aij and F is like some fixed constant, some constant. And let's say it's changing very nicely around there. Okay? So I just try to give you a philosophy. Then if you choose a very small neighborhood around there, so you choose a very small neighborhood, then the change of the coefficient is very small. Okay? So the regularity of the coefficient will create small perturbation. Okay? So it could be C2 function or C2 alpha, whatever, C alpha or LP space and so on. Okay? So you make a small perturbation. So if we have some regularity on the coefficient, then we will have small perturbation in a given space. So then, well, if Aij and F is a C alpha, okay, it means F is a C alpha is f of x minus f of y, x minus y, alpha. So x is different, y This is constant. So in other words, the value of f at y is converting to the value of f at x with this fashion. So this one implies. So this one is called order continuous. Okay, order continuous. So order continuous means your function is converting to the certain given function in continuous way, but there is a decay rate, just like order function. So if alpha is half, then it looks like this, half. And if alpha is 1, then it's left. So that is a kind of small perturbation theory, and then what you want to say is the solution is C2 alpha. Okay, and that is a so-called the Schauder theory. Okay. So why is it C2 alpha? Well, you can guess it. So for example, the simplest PD is ODE. So you think this is f of x. Let's say this is C alpha. Then your second differential is Holder function. So it means you will be C2 alpha, right? So, when you try to prove something, then think about the easiest one. And then you guess what the answer will be. Okay, then actually you try to prove the complicated one. Okay, so this is the one I need to look at. And this is a small perturbation. And then, so your environment is changing very nicely, or your domain is changing very nicely. Then every such nice change will create such a smooth or certain continuous coefficient. But sometimes we have a very large perturbation, like we may have a random effect. Okay, you don't know what's going to happen in your next point. Okay. So for example, so it's just a bounded function. Psi I and psi sub j is a large psi square, and okay. So the eigenvalue of a sub ij is a fluctuating between small lambda and large lambda. Okay. So in the other words, a sub ij has a very large perturbation. I don't know. Yeah. So, and it doesn't have any continuity, it's just bounded. So it's a large perturbation. Okay. So then we can show if U is bounded in, let's say, larger ball, then solution is order function. Okay. So if your equation is lambda of this type, and there are two cases. The first one is, let's say, a sub ij over x and d sub ij of u is 0. Then bounded function implies u is C alpha in smaller ball, and that is called Karloff and Safanov theory. And if it has a divergence type, and that is called, the same result is called the Zoji. Spelling is confusing. And Nash also theory. And autoregularity is very important. Why is that? So let me give you one remark. So let's say you have some sequence of functions, and let's say your hormone is uniformly bounded. Okay? Then you have limit, which is C alpha, and this one converges to U uniformly. Okay? Because if U sub k is here, let's say satisfy this condition, and let's say U sub k is uniformly bounded, then this one implies the sequence of the sequence of U sub k will be equicontinuous. So then you can apply Azala's Schauder theorem, then you actually can extract convergent subsequence to a certain limit. And then all of the regularity argument our experiment is a really approximation. Okay, our data has a certain noise. Our coefficient may have noise. The question is, even though I make a certain noise, let's say if I reduce my noise to the true value, then can my approximation converge to the real one? So the convergence issue is a very, very fundamental issue. And you try to find existence. Okay? So basically, for the continuity will give such a result. But this one has a really deep theory. Okay? And then, so that's what we're going to learn, basically. So today, I will discuss Schauder theory in a very short time. And then I will discuss Kirov-Sakhanov theory and dissociation theory in coming lectures. So, let's think about Schauder theory. And there are three main steps. So let's say you have equation A sub ij x d sub ij of u is f of x. That's what we're going to consider in this lecture. So then, well, actually in the application, you may end up with the U equation. So it may be very complicated. It may have different shape from this one. So whatever it is, if you try to make a regular theory, then consider the simplest case, okay? And that is called the model problem. So the first one is a regular theory. On the model equation. Okay. So for example, what is the simplest case? So A sub ij could be delta ij, and f is simply 0. Then you end up with Laplace equation. Okay, so that's what we're going to discuss in this class. But there could be different examples. So let's say, so if you look at the Poisson equation or shock front, where the subsonic region meet the sonic region, and the under region, let's say this is sonic region, and this is subsonic region. And then you may consider this equation right here. Okay, so that, or if you look at the curvature flows, whatever, then your A sub ij may have different shapes. For example, what if your A sub ij goes to 0, just like this function with alpha. So this is x, and this is your boundary. Okay? So then your coefficient goes to 0. as your x approach to the boundary. So in the other words, it's very different from the Laplace equation. At a Laplace equation, your coefficient is just constant. It never be zero. Okay? But in this case, it could be zero. And then in the other example, free boundary problem, Gauss curvature flow, approximatives, well, there are lots of different situations. It's like zero goes to zero in different fashion, it goes to infinity, and so on. In that case, your model problem will be changed. So in this example, the model problem will be x sub n to the alpha Laplace of u is f of x. And it's a degenerate equation. And so on. So then you really need to discuss regulatory theory on this problem first. And that is not that trivial sometimes. Okay? So but in our example, this is our model problem. So then u is C infinity. And harmonic function is C infinity. So we don't need to discuss the regulatory theory of the model equation. So that's the first one. So let me give you some remark about the model equation. So one of the way to discuss the regularity of the model equation is you have a fundamental solution. Then let's say this is f. Then u is convolution between the fundamental solution and f is x to the and then this is an integral representation. And then you know how to estimate it. F belongs to somewhere, then you make estimate, then you get a regularity of u. Okay, so if you look at the Stokes equation, then you may have a different column, then you have F, but still you can discuss these issues. And this argument is very general, so you can extend it to the system. But on the other hand, all of your solutions should be represented through the convolution. So it's a really linear theory. Okay? And that is one of the ways to get the regularity of solution. And the other one is the more we call the Bernstein computation. Bernstein computation is, instead of looking at this one, it really depends on the linear structure of the operator, and we look at the different quantity, like Rn minus u squared, A and B, eta squared, and the gradient of u squared. Okay, and the eta is, let's say, here is 1, and eta is a cutoff function. And then show, well, Laplace of g is greater than or equal to 0. So G, that means G is a self-solution. Right? Then max of G on B1 is less than, is the same, is less than or equal to max of G under the boundary. Okay? Under the boundary, this is a cutoff function, the value is 0. Okay? So this one is basically max of, and the B1, A m minus u squared. So it's like a constant UL infinity in B1. Okay? So on the other hand, your cutoff function is very nice. It has a certain value and a half ball. Okay? So then this is greater than max of gradient of u on the half ball. So you can control the gradient in terms of L infinity now. And then if you look at the further regularity, then you simply take another differential, then the max of gradient of u, let's say be half, and right? So because of this one satisfied equation, And this is less than UE infinity of, let's say, B like 304, and CU. Now you apply this one, infinity of B1. So if you apply inductively, then you can control every differentials. But here, you don't need any integral representation. Basically, you need to cook up one sub-solution. So just M is max of U in B1. So you can choose a large number. So that's the philosophy. Yeah, it depends on you just put it there and find A and B so that this is true. Okay. So here the game is finding sub-solution, creating sub-solutions. So it requires a lot of imagination. And here is a real integral transformation. So the question is what kind of estimate will be preserved under the integral transformation. And that's a little bit different philosophy. Okay, so that is the standard theory about the model equation. And then the next one is, so there is the first step, and the second step is approximation lemma. So approximation lemma basically tells you if you perturb your data a little bit, then your solution will be changed a little bit. This is supposed to be, right? So that is approximation lemma. So, and it says the following. So we will consider the simple case. So let's consider Laplace of U is f of x first. Okay. Then I will add up a sub ij later on. So, but this one is the more basic. Okay. So the lemma is the following. There are delta and lambda such that if f of x is true in B1, and let's say L infinity norm of U is less than 1 in B1, and let's say the L infinity norm of f is smaller than delta in B1. Okay? So if f is 0, then we end up with a harmonic equation. Then your solution is very nice. Okay? So let's say f is very small. Then, so if this is true, then there is a quadratic harmonic polynomial P of x such that U over x and P of x and the difference, small about this lambda, is less than equal to lambda 2 plus alpha. So you can find such a lambda and delta. So if you choose a very small delta, then in other words, your right-hand side has perturbed from the harmonic equation with a very small amount of delta. Then your function, your solution, has perturbed from the harmonic polynomial with a small error. So that is approximation. So then proof, very trivial.
So is it 1 or lambda? Out of U.
Yeah, it's less than 1. Yeah. So U is bounded. Then, okay, let me give you a picture. So the picture is the following. So initially you have just U, okay? Then it satisfies almost harmonic function, harmonic equation, okay? So then in a small ball, okay, small ball, you can find a quadratic polynomial, harmonic polynomial. This is a U, and this is a P of X, and the error between them is the size of lambda to the 2 plus alpha. Yeah, alpha is between 0 and 1.
I think the statement a little bit strange. The lambda is in the assumption, but something like lambda is not in the assumption.
No. It's not an assumption. Okay. So it's a little bit confusing. And so you can find the delta and lambda satisfying this fact. Okay.
So you said everything, no?
Where?
So the entire inequality is lambda.
Yeah, lambda.
So it is everything, no?
Oh, yeah, sure. Yeah. I'll finish. Thank you. So well, the idea is pretty simple. If you perturb the equation a little bit, then your solution will be perturbed a little bit. That's what I try to say, nothing more. But I just choose the delta and lambda specifically in this form so that I can get a C2 alpha like a little later.
So if delta is 0, then it's nothing but the Taylor expansion.
That's right. So we will use the Taylor expansion to find this polynomial. Okay. So the first one is, if we find a harmonic polynomial, I'll try to approximate this solution U with a harmonic function first of all. Okay? So let V of X be the harmonic replacement of U. So in other words, here is the radius 1, and the Laplace of V is identically zero in V1, and V is the U under the boundary. Okay. So in other words, if you have a U here in 1D, and what is the harmonic function in the 1D? Straight line. Right? So you choose this endpoint and make a straight line, and this is your harmonic replacement. Okay? So then if you choose this view, then claim is the difference between U and V, and L infinity only V1 is a constant times delta. Okay? Because you change the F with a small number of delta. So even though I'm doing Schauder theory or C to alpha regular theory, then the same philosophy can be applied to different estimate, W1P or W2P and so on. As long as your coefficient has a regularity, then it is like a small perturbation. So you freeze the coefficient, get the regularity of the Moore equation, make a small perturbation. So always you have approximation lemma. In maybe different form, but basically the idea is the same. Now, so I'm talking about the L infinity now. So I'm going to use following fact. So let H positive is V of x plus delta 1 minus x squared and 2n. Okay, and this one will be a super solution. So if you apply Laplacian, right, then Laplace of v is 0. You take a second differential and take a trace, then it's going to be delta. And it is Laplace of is minus delta, and that is less than equal to f of x, and that is Laplace of u. And then u and h plus is the same on the boundary of v1, because here this value is 0, and the v is equal to u, so they will be equal. And this is a super solution of this u, and they have same value, therefore u is less than equal to h plus on the boundary, on the whole integral in the domain. And that one is less than equal to v of x and constant delta. Okay. So similarly, you can show u is v of x minus c delta. So it's done for this proof. So in other words, if you change f a little bit, then your solution is very close to harmonic function with this error. Okay? But I need to find specifically quadratic polynomial, because I'm going to discuss the C2 alpha regularity. I will tell you why I need a quadratic polynomial later on. So and the second part is let quadratic polynomial is v of 0 and div at 0 and xi and half dij v at 0 xi and x. Okay. So then it is a harmonic quadratic polynomial. And why is it possible? Because my solution has a regularity. Yeah? So v is harmonic function is a C infinity. Okay? That's why I'm able to write down in this form. And also, we know v of x minus p of x is smaller than constant x to the 3. Okay? Since v is a C3. At this step, we use the regularity theory about the Moore equation. Okay. So then, now I combine these two results. And u of x minus p of x is less than equal to u of x minus v of x and v of x minus p of x. And then this one is smaller than C delta, and this one is smaller than C x cubed. And then this one will be smaller than C delta, and the C lambda to the 3 in B sub lambda. And then you can choose lambda So select lambda so that this is true. And B sub lambda. So it's done. So now, the third part is apply the approximation lemma so that we have a sequence of harmonic polynomials k of x is a sub 0, a sub k, and b is I k, xi. I have ci j k, xi, and xj such that and my statement is started here. If Laplace of u is f of x, and the u infinity b sub 1 is less than 1, and f of x smaller than c x to the alpha, in the other words, is a whole function. Okay? So then u of x, pk of x, and the b sub lambda k is a lambda k to the 2 plus alpha. So, and the idea is pretty simple. Let me tell you what it means. So, and here we had a u, right? And at one step, I found a piece of 1 of x, which is a harmonic polynomial, and the error between this function is a harmonic polynomial, and the u is smaller than lambda to the alpha, 2 plus alpha. And if I choose lambda squared, then I want to improve my approximation so that in a small one, and my approximation is better. So then the error between them is a lambda squared 2 plus alpha. Okay. And this one is my second harmonic polynomial. Okay. So I will go into approximation lemma inductively so that I can choose better and better harmonic polynomials. Okay. And so that the error is small. And also, the harmonic polynomial itself is close to each other. So in the other words, and bk c lambda k 1 plus alpha ck plus 1 as this error. And if this is true, then what we're going to have corollary. You just harmonic polynomial p of x such that u of x and p of x of infinity in the b sub r is less than c r to the 2 plus alpha. Okay. So in the other words, you have solution u, and then you have approximation p of x, harmonic polynomial, and this error, this is lambda, this is r, and this error is r to the 2 plus alpha. Okay? And that is C2 alpha estimate. Okay? Well, I can tell you more, but we don't have enough time, so this is more or less, but there is a small argument. Basically, this one says the second differential polynomial is constant, and times 1. And 1 is our infinity, basically. So this is true. Okay. So why is that true? Because you're decreasing the radius of the ball geometrically. Then the error is decreasing radius to the 2 plus alpha. That's what it says. Okay? So if you look at this estimate, then it's done. Then it's pretty easy to show it. So let's assume that is true. Let's say this is the second statement. So that is true. True. And I want to say it is also true at the next step. So if I want to apply approximation lemma, so the our infinity norm should be less than 1, and also your right-hand side should be smaller than delta, right? So that's what the requirement. So first, let's say this is delta. This is nothing. So then let our scale do the function. So basically, I want to see the error of this function. Okay? And then currently the radius of the ball is lambda to the k. But if I want to apply previous approximation lemma, the radius is supposed to be 1. Okay? So what I do is I look at this picture and then make it magnify so that the size become 1. Okay? So in other words, this is u lambda k of x minus pk lambda k x, and for x is less than 1. Okay? If x belongs to the b1, then lambda k to the x belongs to this over lambda k. Okay? So that's one of scale. And then the other one is I need to make it the size is less than 1. So I divide it with that number. So I divide all of the number with the lambda k plus to the 2 plus alpha. So now let's apply Laplacian here. Then, so you take a second differential is lambda k square and the Laplace of u, and this is harmonic function, so it's 0, right? So it's lambda k, where is it? 2 plus alpha. So 2 really goes away, and this one is f of lambda k of x and lambda k. And if you take absolute value of them, and that is smaller than delta, and the lambda k, here is alpha, x to the alpha, lambda k to the alpha, and that is delta absolute value x. But this one is smaller than 1, so it's smaller than delta. So it fits with the assumption of the approximation lemma. So you simply apply approximation lemma on v of x, then existing q of x such that v of x, q of x is of lambda is less than lambda 2 plus alpha. And what is this? This is lambda k 2 plus alpha. Now you have u of x lambda k and the p lambda k of x minus q of x and this of lambda. And then now this one is supposed to be, and then you multiply this one to here, and this is your u y. Then p, the next, this is piece of k plus 1 y is p k of x y, and oh, I'm sorry, this here is the q, right? And 1 over, then this is lambda k 2 plus alpha q x over lambda k, right? And this is your next polynomial, okay, y. Okay? And the coefficient changes a little bit. So, and that's the story if you perturb f. And then let me give you one remark. What if you perturb diffusion coefficient? So now let's consider this one. And let's say a sub ij at the center is delta ij. So then Laplace of u is delta ij, d sub ij of u, and they are equal. So what I do is f minus a sub ij of x and d sub ij of u. Okay. So then and this one is delta ij, aij, diju, and plus f, and this is your u, f tilde. So then there are two ways to treat these issues. The problem of this problem is this one problem. So the second differential goes to like the distance x boundary base of 1 square. So if you are infinity known is bounded in B1, then you can make an estimate of the second differential in the inside. But you cannot control the second differential all the way to the boundary, because under the boundary you just have a continuous function. Okay? So it's impossible. So your second differential blows up as you approach the boundary. So then f tilde will blow up. Okay? To treat that issue, there are two ways. One of them is So method 1 is basically it's approximation. Here is B1, and you decrease your radius a little bit with eta. Okay? And the interior, this one is control. Okay? Even though it is a large value, but anyway it is control. And your function, this one could be very small. So here, second differential of u is like c eta squared. But a sub ij, delta sub ij is square of u. It's like, let's say this is smaller than delta, and this is c eta squared. So you choose delta. Okay? But what about the error? Because you went inside. Okay? So then still here, and then u is the solution, and v is the harmonic replacement. And v is not very nice all the way to the boundary. The u could be bad, but still to the boundary. Then u and v, the error of u and v is like c eta to the alpha on the boundary of this sub eta. Okay? So your harmonic replacement and the solution has a little error if you have a curve and Saffonov foil all the way up to the boundary. So then here you use approximation lemma and you follow the same idea, same steps. Then it's done. Okay, that is one of the way. And the other one is you choose different norm, which allows the blow up to the boundary. So that is an interior norm. And that is my last remark. You star of C alpha is supremum, and you allow the blow up. Okay, so that is the second differential. So u L infinity and du L infinity, and the second differential, let's say 2 alpha. Okay. U is L infinity. Here supremum, and you allow the blow up of the solution up to the boundary, d sub 1 and du of x, and the supremum over b1, and this one blows up quadratically, and the supremum x different y. Two plus alpha, and the standard part. So if you delete this part, then it's a standard C to alpha norm. But now this one goes to 0. So in the other words, this one goes to infinity as your point approaching to the boundary. So this interior estimate, interior norm, allows the blow up each differentials. And if you use that norm, then still you can carry out, you can take care of the blow up this part. And that's 2 tricks. Okay. And that's the end of the